Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Caroline Haslebacher with us today. Hello, Caroline.
Hello, Frank. Thanks for having me. It's an honor to be on your
Well,
series today.
thank you so much for agreeing to talk about your very awesome article, which I think will have something to do with that poster over your right shoulder, if I got the parody right.
Yes, that's right.
Very cool. Caroline, what's your geolocation?
I'm at the moment in Boulder, Colorado, in the US.
In the moment. So where's not in the moment usually?
Oh, no, that's where I moved to
Ah, okay.
7 months ago. Yes, I'm doing a postdoc here with Lisa Roden. Yes, on a Swiss fellowship.
Yep.
Yes. So
Very
I was moving from Switzerland.
got it. So you're a freshman PhD?
Yes. I graduated last September.
Congratulations, Dr. Caroline.
Thank you so
That is
much.
awesome. That is really awesome. Very cool. Well, I do hope so. It is July 9th of 2025 as we record this, and I do hope you are enjoying a little bit of mountain high weather there in Boulder.
I do. Today is the hottest day this summer.
What's
uh,
the what's the temperature there today?
37 degrees centigrade.
Yep.
So yes,
That is a little warm for Boulder. Yep.
yes.
Yeah.
But
So I'm
it's
in.
also very dry, so you don't feel it as much. Yeah.
That's what we tell people all the time. It's a dry heat. You won't feel it. So I'm in Phoenix. We are definitely in the 40 C range plus, 110
Wow.
F or so. So yeah. But the summer is actually when Phoenix gets it's the moistest is in the summer because the stuff's coming up from the Gulf, so it carries a lot of moisture. But yeah, either way, it's still warm in summer. Very cool. And Caroline, what do you like to do for research?
I like to work on Europa, which is
Cool.
also the focus on of my PhD. And I like to develop tools and frameworks to help the next mission, Europa Clipper, that launched
Nice.
October,
Nice.
help analyze the images that we get. So I'm an affiliate on the Europa Clipper, um, well, the camera team, so the Europa Imaging System
Yep. Yep.
instrument team. Yes. And yes, so I really love deep learning applications. And so I digged into that during my PhD and tried to combine these two. And
Beautiful.
yes,
Beautiful. And we're going to cover this. Very
yeah.
cool. And that is going to bring us to this very awesome Planetary Science Journal article. It is open access. It's the open access air, people. You can go grab a copy for free. Go get one. Length, width, and relative age analysis of lineaments in the Galileo regional maps with LineaMapper. And Caroline, take us away.
Thank you so much. First, I'd like to give a shout out to my collaborators, which are awesome and excellent. And I learned so much from working together with them. Javier, who developed actually the whole LineaMapper version 2. I have to acknowledge his work.
Good.
Was excellent. And then with Louise Proctor and Erin Leonard, we talked a lot about the mapping process.
Mhm.
And also with Alyssa
Oh,
and discussed the results.
mhm.
And last but not least, my supervisor, my PhD supervisor, Nick Thomas, who came up with this whole, um, well, basic idea. Yeah.
Great shout out. Great shout out. Okay, let's
Thank
get to
you.
it.
Yeah, so this article, um, I gotta be honest, I back in September, October, when I just graduated, I thought this would never come out.
Oh
And here
no.
it is. Yes, so it was a lot of work, but I'm very happy with the result. And so
Oh,
I
good.
hope that also through this series, people hear about it and will use what we produced.
Good.
Yeah. So what did we produce?
Yeah, what did you produce? Why are we doing this? Okay.
Yeah, maybe first, why are we doing this and what? So, yeah, maybe figure one would be a good start.
Figure
So,
one. Let's go to figure one. I'm going to zoom out to get a global here and global regional maps.
yes, okay. So first, let's look at the base map of Europa. And you see at this scale of, okay, 500 meters per pixel, but not on your pixel screen, of course.
Not here. Okay.
You see Europa is crisscrossed by lineaments, which we
Yes.
think
Yes.
these lineaments evolve out of fractures, maybe related to the tidal stress field of Europa,
Hmm.
and into these large and different forms of lineaments.
Okay.
But
Okay.
so here we see Galileo coverage in the black and white image on top, and the red, yes, the red regions are
Uh-huh.
the regional maps of Galileo. So that means we are looking at the regional scale of 215 meters per pixel.
Got it.
And then you also see this red cropped region, yeah,
Yes.
of the southern leading hemisphere.
Hmm.
And so we have tried to map for the first time all identifiable lineaments in this region.
Gotcha. I'm with you. Okay.
And we had the help of the first version of that deep learning tool that I was developing,
Hmm.
which is already published in another article, and it's called LineaMapper. So if you Google LineaMapper, you should find the article from 2024.
Cool.
And we used the output of LineaMapper version 1 to help us map a bit faster
Okay.
because we're already guided by some lineament mapping.
Yes. 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 Okay.
Okay, and then okay, no, before I do that point, maybe focus on the bottom part, which
Hmm.
showing the global geologic map by Aaron Leonard et al. 2024.
Good.
Basically, you see two colors, blue and green.
Okay.
And the green is the chaos region, which we will see a bit later. But it's
Good.
basically, um,
Uh-huh.
you can say it's more chaotic than the blue, and
Okay. Okay.
would have been easier to start with the blue. So the blue are the ridged plains, and
Okay.
this really just means crisscrossed lineaments all everywhere.
Okay.
And we think that the chaos terrain has um, melted up the
Ooh.
ridge plains
Okay.
and
Okay.
produced chaotic material.
Okay.
And in this article, we have found evidence that this is really the case. And
Ah.
finally, we were able, based on all the statistics we put together out of this lineament map, that's why we did all this mapping, we were able to hypothesize that younger features are stronger and survive chaos formation more likely.
Got it. Cool. Nice. Very nice.
That's like the big picture.
Mm-hmm.
And yes, as I said in the beginning, I really hope that people are using these products we have um, given. And so maybe we can go to figure 5 now,
Thank you.
where you
On.
see the
Okay.
southern leading hemisphere lineament map.
Ah, yes, the red
Yes,
region that was boxed out. Okay.
exactly. So we are now in that southern region of the regional maps.
Yes.
And the different colors just mean the different categories of lineaments, which we will
Yes.
cover in a second.
Okay.
But
And
it's just important to see there are different lineament types.
yes.
And what you also see is that the bottom is much more colored than the top, right?
Yes. Definitely.
Yes. So it's much denser. And this is exactly because the top is a chaos region and the bottom is the rigid planes,
Gotcha.
which is
Yes.
also shown in outlet B.
And the geological context here, right?
So all the green part is the chaos region.
Uh-huh.
The point is that no one has yet gone in and tried to map all the lineaments in the chaos region. And I thought this yeah, could be valuable to find out more about lineament formation and evolution and chaos formation.
Absolutely. Very cool. Good. I'm with you.
Okay, then in outlet C, if we're in this figure already, I
Yeah.
can explain that, okay, as I said, we used LineaMapper version 1 output to generate this southern leading hemisphere map that you're seeing in
Okay.
outlet A.
Mm-hmm.
And now, what have we generated as well? More training data for
Okay.
a better version of LineaMapper.
Cool.
So what you see here, yeah, on the left is the which regions we have used for training and testing.
Okay.
Yes. And then region A we will see later in another figure. So we have used that
Yeah.
to qualitatively show what the output looks like.
Good. Very cool.
Okay, now we can go on to figure 30,
Figure 30. Let's do a
because now we can even zoom out more and feed in the whole regional maps. Now that
ooh.
LineaMapper
Ooh.
version 2 or version 1.1,
This one's
uh,
one.
I will cover the difference. Um,
Okay.
now that we have these,
Nice.
spec well, they are now specified to the regional maps resolution. We
Cool.
can let them loose on all data we have at
Yeah.
this resolution.
Training and otherwise.
And this is the output.
Very cool.
Yes, and so
Very cool.
outlet C and D just show you like,
Level of detail.
yes, exactly, thank you.
Very cool.
Exactly. Um, to make this happen, I had to come up with an algorithm to stitch the individual tiles together.
Yes.
And this is maybe the one thing that could be still improved. So if you look now at the output, you will see, like in a GIS application,
Okay.
you will realize that there are, well, this is not perfect, of course. However, it might still help you map faster or see correlations or map out other features in these maps.
Okay.
Yes.
Okay. Fair enough. Fair warning.
Yes. So I have provided these on a Mendeley data repository that is open source.
Very
So
nice.
yes.
I'm a big proponent of open source, so I'm glad you're putting it out there.
Yes.
Very good.
Together with all the code and all things that I considered useful are useful for reproducing part of this study.
Yes. Cool.
Okay, I hope that gave a big picture.
Yeah, I got a big sense of what's going in, and then we have LineaMapper and then the output. So yeah, I think that's a great summary of input and output. Hmm.
Okay, thank you.
High
Okay.
level. Very
Now I have not told you anything or shown you any real images of the lineament categories,
yes.
nor the ridge plane versus chaos. So let's do that
Okay.
with figure 2.
Figure two. Let's blast up to figure two. And figure two, ooh, a selection of features. Here we go. What these things look like.
Yes. Okay, so in A, you just see generally how do the ridged planes look like, and now you already suspect, yes, that's the 10-kilometer bar. Thank you.
Mm-hmm.
Um,
Mm-hmm.
you might already suspect that it's very hard to map all identifiable lineaments in the ridged planes because there are just endless.
Too many of them.
Yes. And
Yeah.
also we are really going down to the
A
noise.
certain scale, right? A certain spatial scale. So yes.
Yeah. Um,
Mm-hmm.
Having said that, this will, on a side note, we will get a global scale of Europa at 100 meters per pixel with Clipper. So this
Ooh.
will be
Mm,
updated, and that's my hope with LineaMapper to be able to do that in an automated way.
very cool.
So it's
Nice.
preparation for Clipper.
Yes.
Okay, so that's the ridge planes.
Okay.
Then there are bands,
Mm-hmm.
which can extend really to a few tens of kilometers, as you see. So in the middle tile,
Mm-hmm. Very clear there.
the band doesn't even stop when the image stops.
Yeah. Yeah.
So it would even continue. We don't know how much further, but yeah, this is a really large band. But there are also smaller bands, like in the left tile.
Yes.
Yes, they have like this smooth, well, on this pixel scale level,
They look
they
smooth.
appear smooth.
Yes.
They might be lineated, and we think they're, well, these are dilational features, so spreading features, but there are also some that appear to be contractional features.
Okay. 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 So crust is still moving around.
Yeah, that's what
Yes.
we think at the moment. Yes.
Mm-hmm.
Okay, then next are examples of chaos.
Chaos.
Um,
Okay. Eek.
well, as a large unit,
Mm.
and the middle tile displays micro features
Yeah.
or smaller pits and
Yes.
domes. Yes.
Mm-hmm. See this very clear. There's
Oh,
a shadow line. Yes. Mm-hmm.
yeah. So yeah, they they are just inside the ridge planes, the middle micro features one. And the left and the right, they show chaos terrain, well, the unit itself. And you see this matrix material, and you can identify some lineaments, but it seems
Yeah.
like it could be melted, broken up, and resurfaced.
Okay. Okay. Yes.
Yes,
Something
but
going on there.
there are still lineaments in there, and
Mm-hmm.
so yeah, that's what
Yeah.
you're interested in.
Clearly see some there in the middle. Okay. So we got bands and chaos and planes. Yeah.
Then we also got double ridges, which are the most ubiquitous
Good. Yes.
feature on Europa.
Uh-huh.
It's like um, a
Yeah.
graph in the middle and then two ridge crests. And they can be very long, but also very short and narrow. So they appear on all scales
Interesting.
and everywhere. And
Hmm.
we do not know how they form up to this.
Yeah, that's a
There are
mystery.
plenty of hypotheses, but none is confirmed. So I think we have to wait for Clipper.
Oh, we'll come back to that. Okay.
Yeah.
Very good. Okay. Double ridges.
And then next are ridge complexes, which are really a category that you could think of. They look a bit like bands,
Sort
but
of.
a
Yeah.
bit more chaotic. And really, the definition is that it's multiple double ridges
Okay.
that interlace.
Okay. Okay. Good. Yes. I can see that. That's a nice definition.
Okay.
Clear anyway.
And then, of course, there are troughs, which are very narrow cracks, we think,
Yes.
in the shell, and they may be very young.
Yes. Okay.
And last but not least, everything that we cannot identify
Yeah.
on scale,
He's G.
we term undifferentiated lineae.
Yeah.
But for some of these undifferentiated lineae, you can really almost see a double ridge structure. And so we think that most of these are double ridges if you would have higher resolution.
Yeah, that makes total sense. Right. So for
Okay.
example, if you took this one and sort of degraded the spatial resolution, it may well look like one of these.
Yeah. Yeah.
Yes. Okay. But a catch-all category, undifferentiated. Okay.
Yeah. Yes.
Thank you. Now I have a good
Very,
sense of
very important to
the
have.
features on Europa. Okay.
So troughs, we also mapped as undifferentiated lineae, not to make another category for LineaMapper.
Okay.
But they could be reclassified, of course.
Okay. Oh, so these are the these are the seven features that go into LineaMapper. Mapper.
Okay, so maybe that's a big
Or
confusion,
out.
but A and C are units, basically,
Okay.
and B, D, E, and G are what we actually used for mapping.
I'm with you. Very cool. Thank you.
Yes. Thanks for asking.
Sure.
Okay. In the interest of time, I would say we jump directly to see how well the retrained version of LineaMapper did on these examples.
Okay.
So chaos versus ridge plane, which we will find in figure 11.
Okay. Let's slide down to figure 11. And we'll get there somewhat quickly. 6, 7, 8, 9, 10, and 11. Comparison of the different versions. Might be good.
Okay.
What is different between the versions?
Yes, first of all, very good question. Okay, we have on top, you see version 1, 1.1, and 2.
Mm-hmm.
There is a table that would explain that, but well, I can explain.
We can go to the table if you want.
I think I'm good for the moment.
Okay.
Yes,
Well,
okay, so LineaMapper version 1 is exactly what we published back in 2024
yes.
with the first publication. So this is actually what we used as a guidance for generating or mapping the southern leading hemisphere map that
Yeah.
we saw first in figure.
Yes. Mm-hmm.
Okay, then version 1.1 uses the same architecture as version 1, which is the mask RCNN,
Okay.
published by He et al. In 2018.
Mm-hmm.
And the only difference is the training data. So we
Got it.
use then all of the southern leading hemisphere, which we call the revised map because we revised it
Right.
from
The area got a little bigger. Uh-huh.
and
Okay.
version 2 is a completely different architecture.
Okay.
This is based on the very recently released segment anything by meta model, or short SAM.
Okay.
And
Okay.
yes, and so the training of that uses the same training data than version 1.1,
Yes.
but wholly different
Cool.
architecture.
Good. Good.
And what we will see here is that the architecture doesn't make it, like the new architecture doesn't make it actually better. That's the whole point of all the figures in between, which
Yes.
call out the metrics and the performance, analyze this in detail, and talk out why.
Cool.
So for the interested,
A lot of details in there.
yes, there are plenty of details. Yes. Okay, so what do we see in this figure? On the left-hand side, we have the input image.
Yeah.
And importantly, this is an image that none of these networks has been trained on, because that could lead to, or if there was
That's interesting.
overfitting, then that would be better than, yes, on the
Yes.
independent
Yes.
test tile. So these are test
Yes.
tiles.
Mm-hmm.
Okay, and then in the upper half we have examples of ridged planes. So there should be, yeah, there are a lot of lineaments. And then on the bottom or chaos.
Mhm.
So we note that the chaos tiles, they have less color, just as on a big picture scale, than the ridge planes, which we would expect because we know
Yes.
there are more lineaments in the ridge planes.
Yes.
Okay, now if you go up again, so
Yeah.
we
Want to see the ridge planes? Okay.
yes. Okay, and then so we have the output of version 1, 1.1, 2, and then on the right-hand side, the ground truth, which is really just the revised map. So the human mapping.
Got it. Got it.
Okay, so now I have done that quantitatively in these metrics, but qualitatively we can look at these and see which version got what of the ground truth.
Yes.
And now I'd like to stress that the ground truth is not the holy grail. Each mapper would produce a different ground truth,
Okay.
and it's really difficult to at the noise level decide, is that a lineament or not? Am I going to map it, and where does it stop, and all of that?
Yes.
Yes, so with that in mind,
Okay. Thank you for that caveat. Okay.
we see that version 1.1 and 2.0 produce very similar results.
Yes. Let's go here. Toot, 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 toot. Toot, toot. Yes, they do. A lot of the same features.
And what is also really cool is
Okay.
to see that cross-cutting relationships are oftentimes mapped as such. We haven't talked about that at all.
Okay.
But in the title, it said we are also investigating relative age.
Yes.
So how can we do that with just looking at images, right? I should explain that.
Tree rings, tree rings.
Yes, almost, almost.
Right.
So if a lineament forms first and evolves into a full-fledged band
Okay.
as the third row, for example, and
Yes.
then something happens, we don't know what, yet that the purple diagonal one. So
Mm-hmm.
let's say that
Mm-hmm.
comes
Yes.
first,
Beak,
and
beak, beak.
then the green in the perpendicular to it
Yes.
one is overlaying that purple band.
Yes.
That's called a cross-cutting. So based on these cross-cutting relationships, we can say this is younger, this is older, relatively speaking.
Yes. Relatively. Right. Right.
Yeah, that's why it's called relative age.
Mhm.
And what's new in this publication is that we have tried to quantify this by taking the fragmentations per kilometer. Okay, I have to
Okay.
explain a bit
Okay.
more.
Okay. Okay.
Okay, so um,
So,
if we just count how many fragmentations, how many cross-cuttings does a lineament have,
okay.
then we know that the more cross-cuttings there are, the older it is.
Okay. Yes.
However, we have to weight that by its length, because the wider the longer it is, the more probable cross-cuttings happen.
Correct. Correct.
So
Yeah.
it's very easy, just count the number of fragmentations and divide by the length of the full lineament.
Normalized to
That,
the length. Okay. Mm-hmm. Yeah. Yeah.
that gives us a number. The higher the number, the older the lineament.
That makes intuitive sense. Okay.
Okay, very cool. And this is what we call fragmentations per kilometer,
Got it.
or
Yes.
short FPK. Yes.
FPK. I'll remember. Okay.
Okay.
Patients per kilometer. Okay. Very good.
So, back to these cross-cuttings that are indeed often identified by the neural networks. That's a very good thing. We would like to have that, because that means that we have a framework to automatically assess the relative age of any
Feature.
lineament.
Yes.
on a global scale.
Yes. And that is pretty cool.
Yes. I have to say, it's well, it's not yet perfect. The metrics could be higher, so there is room for improvement,
Of course.
but that's the vision.
Mm-hmm. Mm-hmm. We're well on our way to that one.
Yes.
All right. Very cool.
Okay.
Beautiful. Beautiful. Beautiful.
Okay, and then in the chaos terrain, I'm very pleased that none of the neural networks of these three models mistakes a lot of chaos blocks or other linear looking features for
Right.
actual features.
Mm-hmm.
And in the top row, it's even very interesting to see that this very fine trough here
Yes.
has been picked out by version 1.1 in that
Yes.
case.
And only version 1.1.
Yes.
Mm-hmm.
There is a box for version 2, but no mask, which just means well, it has detected something, but it's not confident enough to tell me,
How it is.
basically, in
Right.
easy words.
Okay. Interesting.
Yeah. Okay. So bottom line is we have tested the newest image segmentation model that there is, which should also be the best. It was advertised at that as a large
Take it.
foundational model. But we have found that for at least for planetary surfaces, the training data makes a higher impact than the architecture.
Fair enough. Yes.
So the metrics show that version 1.1 outperforms the newer version 2.
Okay. That's very interesting.
Yes, that's a very interesting result from this model development perspective.
Because one might naively assume it has a higher number, it must be better.
Yes. Yes, that's maybe one confusion, but 1.1 is just using the same architecture as one.
Uh-huh.
So
But it's
otherwise,
good. It's good to explore different architectures, right? And see where your sensitivities lies and see what agrees and what doesn't. And it's a great experiment.
yes, as outlined in the text, we are not the only ones that have found that this newer architecture, SAM, is outperformed by older architectures.
Okay.
So that was interesting for me to see.
Yes, that is.
Okay, so I think we have talked enough about the model side of things.
Okay.
Unless there is something I have completely forgotten about. But well, I think that's cool for the moment.
Okay.
We can jump into science results. So taking these 2000 newly mapped lineaments from the southern leading hemisphere, so figure 5, we can extract the
Yes.
length and the width and the number of fragmentations, and with that, the relative age.
Correct. I'm with you.
Okay, so maybe we can go now to figure 16.
Yes. 17 and 16, we got some whisker plots. Okay.
So there is almost too much information in these.
Okay.
That's why we have some more plots put in where you see this in more detail, but this is kind of the summary of the whole length, width, and relative
Width
age
and
analysis.
FPK and hence number of fragments. Okay. Very good.
Yes. Okay.
Let's start with explaining the plot itself. Let's go and
Yeah.
let's
Thank
do
you.
length.
Okay. So you
Okay.
have these two colors. You recognize them again, maybe. So we have
Mhm.
blue for the original planes
I do.
for chaos.
Yes.
So the idea is to see how do
Oh,
lineament characteristics differ in regional planes versus chaos
yes.
for these 4 different categories. And that's why I have band, double ridge,
Okay.
ridge complex, and undifferentiated linear.
Right. Category G. Okay.
Okay. And then I have different statistical metrics to
Yes.
be able to easily get a grasp of the distribution without plotting all the distributions
Yes.
each other. Okay, so we have the median, the mean.
Yes.
Then
True.
we did a Bayesian analysis to get
Yes.
out the posterior mean
Yes.
and the um, the 97%
Uh,
probability interval.
there you go. Okay, I'm with you. So there's our black dot there and
Yes. And
97. Okay, I'm with you. Uh-huh.
okay, so that 97% probability interval gives you a sense of how constrained the posterior mean is.
Right, right.
Okay. Um, okay, and so for the length and the width, the main, well, we have tried all different correlations tested, and the main thing we found was that bands show a very similar distribution as ridge complexes for length and for width.
Uh, yes. So this one. Yeah, pretty similar. This
Mhm.
one and this one. I agree. Yes.
Yes, okay, very cool. And so we might think that bands have uh, share more similarities with ridge complexes than we previously thought.
Good thought. Yeah.
So they might share a similar formation mechanism or evolution mechanism.
Ah, very good. Very good. Yes. Yes.
Yes. Or maybe um, it doesn't make really sense to have two distinct categories.
Maybe it's the same thing. Right.
Yes, just a different flavor
Right.
or something.
Right.
And
Yes.
the same, and as I said earlier, we think that most of the undifferentiated lineae are in fact double ridges. And this is also what we see that these two distributions have
There's some
similarity.
similarities.
Exactly.
Yes, between there, and here. Yes.
So that would underline these
Uh-huh.
hypotheses.
Uh-huh.
Yeah.
Very
And,
cool.
and this result I'm using in my current study, which I can maybe say a sentence at the end.
Yes, you will. Okay.
Good.
Okay,
And
then we have the relative age metric. Okay.
okay, so we don't really have to look too much at the plot D because that's just the number of fragmentations. And this, again,
Yes.
divided by the length gives you the FPK.
Right, which is used as the age metric.
Yes.
Hmm.
So the higher the number, the older the lineament. So the
Yes.
bottom ones are very young.
Yeah.
Okay. And now I am um, telling you why we reason
Okay.
that younger features might be stronger and
Okay.
survive chaos formation
Okay.
better.
Yes.
Okay, so bear with me.
I will. I will.
um, if the ridged planes were broken up by chaos formation to produce the chaos unit,
Okay.
then we would expect that lineaments in chaos have more fragmentations per kilometer
Correct.
because they
Yes.
were also fragmented by chaos formation itself.
Yes.
But
That is
they do
true.
not. So here either you see that the lowest point in chaos is either below what's in the ridge planes or the same.
Aha. Yes. Yes. Mostly the same.
Yes.
Uh-huh.
Also, the mean is either lower or the
Um,
same,
they're the same.
except for
Yes.
ridge complexes.
Okay. Yes, I'm with you.
Okay. So they do not show what we would expect. Um, Maybe this is because chaos disrupts exactly where there was a previous cross-cutting, which
Ha.
could make it weaker, right?
Yes. Yes, it would. Yes.
Yes, and that could be, that's like one finding. But either this terrain has experienced less fracturing altogether, to
Awesome.
start with,
Okay.
or maybe the older ones have been eliminated by chaos formation.
Right. Right. They've been erased. Uh-huh.
However, we also find that the spread in FPK for chaos is higher.
It's pretty big. Yeah.
Find green points that are above blue points.
Quite.
Yes.
Mhm. Mhm.
And so, yes,
There a little bit.
we think all of this together is evidence that chaos really disrupts the regional planes, and there wasn't anything exotically else there.
Right.
It had maybe the same, um, well, the same characteristics that that this huge chaos region resurfaced.
Okay. Yes. 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 Old ones got removed. New ones came in.
Yeah, and we
Got it.
have illustrated this in figure 27.
Very cool. Very cool. Okay, figure 27. Let's slide down somewhat quickly. Figure 23, 24, 25, 26,
Yeah, so these are the ones.
27. Ooh, the scenario. There we go.
Yeah, so just to illustrate that a bit more. So imagine that, yeah, in A, you have a band that forms on top of even older terrain.
Okay.
Now we think that band forms due to subsurface events, maybe spreading, as I said,
Like
or
right
maybe
here.
warmer ice bottom, or convection happening.
Mm-hmm.
Okay, then in B, yes, time has passed. There were a few changes to the ice shell properties, maybe, or just the tidal stress field, um, anything like that. And a double ridge forms because now the properties or the environment is good for supporting and forming a double ridge. We
Okay.
don't know how this double ridge formed. We just picture something. But
Something.
the important thing here is that now we think that the subsurface structure still supports a tiny bit of that the band structure
Yes. Uh-huh. Uh-huh.
and a lot of the double ridge structure because that's still like active more or less.
Yes. Mm-hmm.
Now I'm going to see the environment changes another time and it favors chaos formation, which might be a melting of um, ice
Yes.
underneath.
Yes.
And
Right.
we think, or it could well be, that
Fractures.
the youngest features, well, they survive chaos formation
Right.
more likely than older ones.
Very cool. That makes sense. There's a certain intuitiveness to that. Okay.
Yes, yes. I mean, this is, of course, not totally
I,
totally new idea. This is
I,
the first quantitative evidence for that.
mm-hmm. Mm-hmm.
And then in figure 28, just for your
Ooh, very cool. Very cool.
um,
Ridge planes and chaos.
yes, okay. So in A, we see
Whoops.
this is at the same scale. And so just for you to imagine, yes, um, you can think that the B has looked like A previously, then chaos formation happened, and now it looks like B.
Correct. Yes. So there's an evolutionary pathway. Yes.
Mhm.
From organized to less organized.
Yes.
Very cool. Good.
Yeah. Okay. So yeah, that's really the main finding from all of these characteristics extraction so far.
Beautiful. That's really lovely.
Thank you. And now, last but not least, um, we can go to figure 14 for a, the last part of this whole framework and idea.
Okay. And 14, there we go. Lineament coverage. Okay.
So, as we have seen throughout this video and this study, there are fewer lineaments in chaos region. I
Yes,
think that's now very intuitive.
that's clear.
Yes. And we can quantify again. So here you see
Okay,
the area coverage, the area covered by lineaments in chaos region is about 15%.
smaller. Hmm.
Yes, and in ridged plains we have way more. An area of almost 65% is covered by lineaments.
And longer.
And
Hmm.
maybe if you zoom in more, it would even be higher, that is to say.
Oh,
So,
if you had the spatial resolution on Europa. Okay. Yes,
yeah,
yes.
maybe. But at this scale, we can use these quantifications to try to use the output of LineaMapper fully automatically
Yes.
to actually say, if I have an image, is this image chaos or ridge planes?
Yes.
And this is exactly what we did in figure 32 and 33.
Okay, let's slide on down to 32. Summary near the end, 33, 32. Here we go, predicted. Okay.
Okay, so this is needs some explanation. Okay, so we see for all of these three sub-images the global geologic map
Yes.
by Aaron Leonard. And then outlined in black, we see the regional maps.
Where you were doing. Yes.
Yes, so that is where we have output of the different versions of LineaMapper
Okay.
1.1 and 2.
Uh-huh.
You don't see that in detail as in the previous figures we were showing, like
Right.
20.
Right. Yeah, yeah.
But we have just given in the
Okay.
individual Galileo images, and then
Okay.
based on the prediction, um, characterized how much area is covered by lineaments predicted fully automatically.
Yes.
Then we have classified based on the finding that 65% of the area is covered by lineaments in ridge plains
I'm
and
following.
50 in chaos.
Yep, I'm with you.
And so that's what these predictive units describe.
Cool.
Yes. And so we see
Yes.
that it agrees well with the global geologic map. So where there is, when it's blue, it should
Yes.
be like the global geologic
Which
map
ones?
is blue. The tiles should also be blue.
Right.
So LineaMapper version 1.1 again
Pretty
works
good.
better.
Pretty good.
Yes.
And
So there
presumably
is
automated
also,
ones go a lot faster than the one on the right.
sorry.
Presumably LineaMapper is a lot quicker,
Oh, yes.
orders of
Yes,
magnitude.
exactly.
Yes. Hmm.
And of course, you can refine these. If you give in smaller tiles, you get a smaller or a better resolved
Sure. Yes.
boundary. And this will be very well for me. I'm very curious to see what happens when we get new data from Clipper and I repeat this story.
I hope you do.
Yeah,
So
yeah.
there's
And so
32 and
so that's the
33.
trailing hemisphere, and then yeah, the next is just the same for the leading hemisphere. And now
Got it.
you also maybe remember the southern part, which was the input for this
Right.
whole story.
Right. Correct. Hmm.
Yes, so I
Very
hope
good.
I have given you a good tour around this study and yeah, spread the vision for these lineament studies.
Awesome. Caroline, I want to thank you so much for walking us through your very awesome article. Thank
Thank
you
you.
so much. Yeah, and you kind of mentioned it a couple of times there. So let me go ahead and push on a little bit of it and phrase it as, where do you think we go from here given the published article? So you mentioned Europa Clipper. Maybe just remind me when Europa Clipper is scheduled to fly and when we might get some 10-meter data that we can put up on LineaMapper. Are there other algorithms to try? Maybe there's a LineaMapper 3 and so on. It's just where do you think we go from here, given the published article?
Yeah, thank you. Okay, so in about 6 years, we will have the first images from Clipper from
Cool.
of Europa, and this will be a very exciting
Right.
time.
Yes, it is.
Yeah, but also requires to be quick in analyzing new images.
Right. Mhm.
And so I hope that LineaMapper, this whole framework, extraction algorithm and stitching algorithm, all of that, all of what we have seen provides a chance to do that.
Mhm.
And
Mhm.
I'm also hoping to develop that further in the next 5 to 6 years.
Mhm. Cool.
So stay tuned. Yeah, maybe
Yeah,
for
stay
the
tuned.
version 3.
So let me drill in on one particular part, right? So we came up with a schematic and some evidence of evolution on the
Yes.
surface.
Yeah.
And do you think that the enhanced resolution from Europa will be able to confirm, deny those evolutionary pictures?
Yes. Not only images, but radar will be very important to
Ah,
answer
yes.
the question. So how does it really look below the surface?
And even just spectral characteristics of the surface could be useful there too as well. So
Yeah.
yeah.
Yeah, there are a lot of unanswered questions for
That's
Europe.
good. That's good.
Yes, there is a
Sounds
lot
exciting.
to explore.
You get to discover something. Yay. Very cool.
But one thing that I haven't, that didn't would have gone out of the scope of this study is to extract the direction of these lineaments. And since we now
Oh,
have these lineament maps,
yeah,
we can
yeah, yeah.
also extract the direction. And
Right.
that's part of where my next research is going, to extract the directions and then see if we can find a correlation with the
Right.
type of stress field.
For example.
And because we have now the relative age assessment, we can also go
Yeah.
back in time.
Yeah, yeah, yeah. Very good. Very good. And you won't have to wait 6 years for that. So
Yeah, yeah.
that'd be very exciting to see. I look forward to seeing that article. Very
Thank
nice.
you so much.
Cool. Carolyn, thank you so much once again. Really appreciate it.
Thank you, Frank, for having me.
Sure. And that will do, everyone. And I hope this made your astronomy Europa Day just a little bit better. And we will see you on the next one. Bye bye.
Bye.